Okay, so let me start off with number 3 again. And see if I can work through 3 through 6 in the next hour here. So just to recap, for part A, okay, we have the spinning toy. We want to find the area of the shaded regions, so we go through top minus bottom. Top being the 6x root 4 minus x squared. And then the bottom function being the 0. Okay, so we know that our area formula is just the definite integral from 0 to whatever that upper bound x value is. Top graph minus bottom graph, top graph being the 6x root 4 minus x squared, bottom graph being the 0. We talked about how in order to find that upper bound, we had to find that x-intercept. So we set the 6x root 4 minus x squared equal to 0. Solve for x. We get 0 for the first portion. The second portion, though, we can square both sides. X squared equals 4, x equals plus or minus 2. So x equals 2. Okay. So once we have our top minus bottom, we're then moving on to identifying the proper procedure to find the integral. We always say that we try power rule first. Can we expand the terms through? But order of operations prevents us from doing that. So we're stuck having to go through our second option, which is use substitution. Get parentheses to show up. Identify the u value to be the 4 minus x squared. And then we go through, make our substitutions, find the derivative, solve for dx. dx equals du over negative 2x. Get this all the way down where we can get our coefficients to be pushed out in front. 6 over negative 2 is negative 3. Integral of u to the 1/2. I can go through power rule. Add 1 to the exponent, divided by that exponent. Flip the 3/2 up to be 2/3. Multiply this out. 3's go away, the negative 2 remains. Bring the original variables back. And now we can work through our upper and lower bounds, right? So upper bound being 2, insert 2 in for x, we get 4 minus 4, which is 0, so that goes away. Minus, then the lower bounds, 0 in for x, the negative, there's another negative here, negative 2 parentheses 4 to the 3/2. Okay. And then we just try to get this down to a number, 4 to the 3/2, the same thing as square root of 4, which is 2. 2 cubed is 8, 8 times 2 is 16. So that's part A. Part A is 16. Part B, it is known that y equals cx root 4 minus x squared. The derivative is in this form. So that's nice. They are telling us what the derivative function is. Okay. Next part, for a particular spinning toy, the radius of the largest cross-sectional circular slice is 1.2 inches. So that means we see that this circular toy has different radius, right? But then the maximum radius is going to be a 1.2. Now the maximum radius, what is that relation to the derivative of this function? The maximum radius is going to occur when the derivative of this curve is what? Is equal to 0. So that's the connection that we have to be able to make. That it's like, how do we get this derivative function in relation to what I want to achieve? And I know that I'm going to be able to achieve that slope 0 right when the radius hits its maximum, right? We're taking this, we're rotating around the x-axis. We know the maximum radius will occur at this point, which according to this curve will be where the slope is 0. Okay, so for part B, we're going to be setting our dy dx equal to 0. Okay, because that's where the meeting point is. Okay, so if I set the derivative equal to 0, setting the derivative equal to 0, finding where the slope is equal to 0 is really a numerator thing, right? The denominator equal to 0 is something else. That's telling us where the slope is undefined. We don't want slope undefined, we want slope 0. Okay, so slope 0 well, C is factored out. Eventually we want to solve for C, but at least right now we can just solve for X, right? That's a piece of the puzzle that we need. But we know that negative square root of 2 is not going to make sense because our graph is not in that negative region. So we know our X value is square root of 2. Okay, but we still have to solve for C. So let's go back to our equation. Our equation is y is equal to cx square root of 4 minus x squared. Okay, it says the radius is 1.2 inches. So 1.2 inches, that the radius, that 1.2 is sitting at the y value. So we know that we have our y value. We also know our x value, right? The place where the slope is 0 is root 2. And that gives us enough information to solve for C. Okay, start inserting that in. Okay, so 4 minus root 2 is the same thing as 4 minus 2. 4 minus 2 is 2. We got root 2 here. So C is equal to 1.2 divided by 2, which is equal to 0.6. Okay, part C, for another spinning toy, the volume is 2 pi cubic inches. What is the value of C for this spinning toy? Okay, so we're talking about volume here. Volume, we're rotating this around about the x-axis. So that rotation, we know there's no gap. So we know this is going to be this method, right? So part C, start off with that knowledge. We're dealing with, we're working with this method here. Okay, big radius, top minus bottom. Which is just that. Oh, my bad. We're going back to CX here. What's the value of C? So we're replacing that. Yeah, we can't do 6 anymore. This is a different scenario. We'll go back to C. Okay, set everything up here. So we got to work this out by hand. No calculator. Distribute everything through. We can simply rely on power rule here. Pull that C squared out. Okay, power rule, we get 4x to the cubed. Work all this out here. 2 in for x. Minus lower bound. All 0 out. 8 times 4 is 32. No, sorry, 15. 20. $32. Okay, common denominator is 15. So, make sure getting this math right here. 364. Something wrong here. 2. I messed up here. $67. Missing something here. It should be 64 over 15.
161 is 96 is.
Oh. Okay, I don't know why I typed in the wrong number. Thanks. Okay, c squared pi. Okay, so this is our resulting volume. We know it's going to be equal to 2 pi. Just given to us there, 2 pi cubic inches. And now we just want to solve for c. So get the pi's to go away. Reduce that fraction. And take the square root. They tell us that c is a positive constant. Yeah, c is a positive constant. So because of that, we know choosing between plus or minus, we're always going to choose the positive one. All right. Questions there? Okay, number 4, let f be a continuous function defined on the interval from -4 to 6. The graph of f consists of 4 line segments, 1, 2, 3, 4. Let g be the function defined by the integral from 0 to x of f of t. On what open interval is the graph of g concave up? So we know concavity comes from the second derivative. So I want to kind of build all my relationships here. So I know that g of x is the integral of f, which means that g prime is going to be one level below integral, which is just going to be f of x. And we know that g double prime is just going to be f prime. So we're just making each side go down one derivative at a time. Okay. So we know that this is really the derivative graph for g, right? F is g prime. So I like to label what I'm looking at. Anything above the x-axis represents where my original g graph is going to be rising. Anything below is where my g graph is going to be falling. Anything on the x-axis is slope 0. But I want to find concavity information. So I know that to pull concave up, concave down, points of inflection, it's all going to come from the peaks and valleys of the derivative graph. So here's my second derivative sine line. Maximum is the peak is at -2. There's a valley at 2. And wherever my G prime graph is increasing, that means where my G graph is going to experience concave up. So concave up, concave down from -2 all the way to 2, and then from 2 to 6, concave up. So G of x is increasing because G prime is increasing, therefore concave up. Right, so wherever G prime is increasing, it's going to tell us where G double prime is going to experience concave up, or where the original graph is going to experience concave up. Part B, let P define as P of X equals G of X times F of X, find P prime. Hopefully we recognize this as a need for product rule. So we go through product rule. F prime G plus F G prime all over, oh, sorry, just F prime G plus F G prime. Okay, so here's the work shown. I know I got to go through product rule. So F prime times G plus F times G prime. Replace every X with 3. And then we can look to see how we can replace these with numeric values. G prime of 3. This is my G prime graph. So G prime of 3, I can just look for the order pair. So G prime of 3 is just equal to -3. F of 3, F and G prime are the same thing. So also -3. G of X is defined as the definite integral from 0 to X. So the integral from 0 to 3. So from 0 to 3, we have to find the area and make sure we resolve that. So this is from 0 to 3. Zero to 3 of, yeah, it's going to give us -3.5. Think of this triangle as -2. And this portion as count the squares there, -3.5. We know that 0 to 1 and 1 to 2, they're going to cancel each other out. These areas are the same, and the resulting is going to be this -3.5. Okay. And then F prime of 3. F prime is the slope of my F graph. So F prime of 3, that's the slope of 1 over 1. Okay. Clean all that up, we get 5.5. Part C, find a limit. This is set up nicely for us to apply L'Hopital's rule. Again, careful that you use arrows, not equal sign. They don't like arrows. They don't like equal signs here. So arrows all the way through. Okay, so first thing we do is we evaluate the limit, or at least we try to. Insert 2 in for X. We get G of 2 over 2 squared minus 4. G of 2 is 0. Okay. G of 2 is 0 because that's the area. The area from 0 to 2. The displacement will become 0. I got a positive region. I got a negative region. So I get 0. So I get 0 over 0, which is allows me to then apply L'Hopital's rule. So take the derivative of the numerator, and then in a separate instance, take the derivative of the denominator. So x squared becomes 2x, 2x becomes 2. Reevaluate the limit. We get u prime of 2 over 4 minus 2. F of 2 is -4. And then -4 over 2, which is -2. Okay, so that's our limit. Our limit is -2. Part C, find the average rate of change of G. So average rate of change is, that's another way of saying slope. So let's find the average rate of change first. Change in y over change in x, g of 2 minus g of -4 over 2 minus -4. We get 0 minus -16 over 6, 16 over 6, which is 8/3. Okay, the next part says, does mean value theorem guarantee a value between -4 and 2 for which g prime is equal to this average rate of change? Okay. Average rate of change, that's the slope. Can we guarantee that slope with the mean value theorem? We can, because the problem tells us that our g function is continuous and differentiable. So whatever slope that we see between the endpoints, this slope has got to show up somewhere along the original graph's curve. Okay, mean value theorem guarantees that g prime is going to equal to the average rate of change at least one point between -4 and 2. All right, number 5. Consider the function y equals f of x, whose curve is given by 2y squared minus 6 equals y sine x. Show that the derivative, that's nice. They give you what the answer is going to be. You just have to connect the two with your work. So to find the derivative, we know we have to go through implicit because you see y's all over the place. And the right side, the y and sine x, these are distinct terms that are being multiplied. So we got to go through product rule. So product rule and implicit as we go through our derivative. Okay, so quotient rule here, f prime g minus f g prime all over g squared. My bad. We're trying to show that this is a derivative. We're starting off with this, so we'll do product rule and we'll do power rule. So we start off with power rule. 4y squared becomes 4y dy dx. 6 goes away to 0. These are product rule here. So f prime times g plus fg prime. Y becomes 1 dy dx. We keep the sign plus go back to f, which is y. And then g prime, sine becomes cosine. So now once we're here, let's see if we can bring all the dy dx's together so that we can factor it out and then we can solve for dy dx. And we know we arrive at the answer if it matches what's told to us in part A. Okay, bring the dy dx over all together on the same side. Factor the dy dx out. And then divide the parentheses over. We get a matching derivative. Okay, part B, write the equation for the tangent line. So tangent line requires order pair and slope. Order pair is already given to us. Slope, we can just enter into the derivative into dy dx to get that slope. That should be enough to build our point slope form. Thank you. Okay. Insert the order pair into the derivative. Cosine of 0 is 1. Sine of 0 is 0. 4 root 3 minus 0 is 4 root 3. Do some cleanup. I get my slope is 1/4. Order pair slope, point slope form. And we can stop there for this problem. Okay, part C. Find the coordinates of the point where the line tangent to the curve is horizontal. So that means where the slope is 0, where the numerator is equal to 0. Okay, so 2y squared minus 6 equals y sine x. So slope is equal to 0 when the derivative is equal to 0. So we have to set the numerator of the derivative equal to 0. So that's y cosine of x equal to 0. I know that y is greater than 0. Solve for x here. I get power for 2. Okay, we have the x value. We can find the y value by inserting this x back into the original equation. 2y squared minus 6 equals y sine of power for 2. Sine of power for 2 is 1. We get two different y values here, because if I factor this out, I get 2y plus 3 times y minus 2. I get y equals 2 and y equals negative 3/2. But for part C, they tell us that y is greater than 0. So we're only going to keep 2. Okay, we found the coordinates, order pair, power for 2, 2. Okay, part D. Determine whether f has a relative minimum, a relative max, or neither at the point found in part C. So it's tough to create a sine line with this derivative. So it's almost forcing us to go through the second derivative test. We'll find the second derivative function and see at that point whether we get a positive or a negative concavity. If we get a positive concavity, we know it's going to be opening up. We know it's going to be slope. It's going to be a relative minimum. If we see second derivative less than 0 in the negative region, we know that we must be looking at a relative max. So to go through the second derivative test, we have to first find the second derivative. So this is a mess. Okay, f prime g minus fg prime. Just to find the derivative. Or actually, yeah, f prime g minus fg prime. Now within f prime, I got to go through product rule and chain rule. Sorry, product rule and implicit. So here's f prime g plus fg prime times g function 4 minus sine x minus y cosine x. G prime is 4 dy dx minus cosine x all over denominator squared. That's a mess, but the slightly good news is that at the order pair for pi over 2, it's going to wipe out a lot of terms for us. So cosine of pi over 2 we know is 0. Cosine of pi over 2, that's going to go to 0. It's going to give us 8 minus 1, which is 7. Okay, do all this cleanup here. We get negative 14 over 49. That's a negative value. Negative value means that we're dealing with second derivative, concave down. So if you're staring at slope 0, but also knowing that it's concave down, you know there must be a relative maximum.
I would suppose there's neither.
Oh, neither a relative max, relative min. So the second derivative test is not going to get you confirmation. Let's say the second derivative ends up giving you 0. If it gives you 0, then that's going to force you to have to go through the first derivative test. You have to actually create a sign line for the first derivative and test the signs on either side to see if there is a relative max, relative min, or neither. But second derivative test is not going to be able to resolve that issue of 0. But that would have been mean if they did it to us, having gone through all this pain.
Just to get 0.
Just to get 0.
Now, if it was first derivative test that you did, you have to set y cosine x equal to 0, and then what 4y minus sine x equal to 0.
Right.
Find the points for that.
Find the points for that. But this is a little too complicated for them to expect students to do that, since there's too many variables. So they're kind of forcing you into the second derivative test because of the complexity of the derivative. Okay, number 6. Okay, a medication is administered to a patient. The amount in milligrams of the medication in the patient at time t hours is modeled by the function y equals a of t. Satisfies the differential equation. At time t equals 0, there are 0 milligrams of the medication in the patient. Part A, a portion of the slope field is shown. Sketch the solution. That's easy. The order pair 0, 0, just highlight that point and then just sketch the graph through, let the slope field kind of help guide your curve as you move along. Part B, using correct units, interpret the meaning of limit of t approaches 0 to t approaches infinity of a of t. So that means as time approaches infinity, the amount of medication in the patient is going to keep approaching 12 milligrams. Okay, part C, using separation of variables. So solving this differential equation. Let's go through the steps that I like to go through here. Cross multiply first to at least get all the variables, get the dy and dt all lined up. And then once we cross multiply, we can decide, okay, is there anything else that needs to be done to cleanly separate my y's from my t's? So to do that, I'm going to have to do a double division here. I'll divide both sides. I'll divide this 12 minus y to the left, but I'll also divide the 3 to the right. Looks like this is going to be a natural log. Use substitution. Careful that you don't just say natural log of 12 minus y. The 12 minus y is going to produce a derivative of -1, so that needs to be taken into consideration. Okay. Pull a negative out. Negative natural log of u is a result of 1 over u, 1/3 1. We know 1 turns into t, plus c will show up. Okay. Bring the original variable back, maybe distribute the negative through, and then I decided to just go ahead and solve for c at this point. Right. Replace y and t with 0. Solve for c. We got c equals natural log of 12. Okay, now you could have also raised both sides with base e, and then solve for y first, and then come back around and insert 0, 0. But either way, we have natural log of 12 being our c value. Replace the c with our natural log 12. Okay. We know that we want to solve for y, so we want that natural log to go away. So we'll raise both sides with e as the base. We get 12 minus y around in absolute value bars. And the right side, e to the a plus b is equal to e to the a times e to the b. Okay. I'm sure we understand that property there. And then e to the natural log of 12, this cleans up to be 12. Hold the coefficient down in front, drop the absolute value, and then we get y is equal to 12 plus or minus 12e to the negative 1/13. Now, which one do we choose between the plus or minus? We want to see which one satisfies the order pair 0, 0. So if I plug 0 in for t, I do get everything cancel out to be 0. But if it's plus, then I get 12 plus 12, and that's not going to be 0. So that's part C. Okay, part D. A different procedure is used to administer the medication to a second patient. The amount is modeled by y equals b of t that satisfies the differential equation. dy dt equals 3 minus y over 1 plus 2, or t plus 2. At time t equals 1, there are 2.5 milligrams of the medication. Is the rate of change of the amount increasing or decreasing? So it's asking for the rate of change, which is dy dt. Is it increasing? So it's asking for the second derivative, right? This increasing of a rate, we got to make our way to the second derivative. So we'll do d2y over dt2. Okay, the 3 is just a constant that'll go away to be 0. But here we got to go through implicit again. F prime g minus fg prime all over g squared. Now, once you find the derivative, okay, y becomes dy dt g minus fg prime all over g squared. To make it easier to work with this, let's bring the dy dt back in terms of the original variable. So I brought back the 3 minus y over t plus 2. Okay, it's a mess, but what we're going to do is replace every t with 1, replace every y with 2.5. And let's see what we get. We get 2.5 over 3. Times 3, we get those to cancel out. My numerator is going to end up giving me negative 9 after I subtract the 2.5. But ultimately, the most important thing that comes out of this is the fact that it's negative. Because our second derivative is negative, we know that the rate of change of the amount of medication in the second patient is thereby decreasing at t equals 1. (2021) is not a fun year for FRQs, but they really packed a lot of things into this FRQ. Okay, any questions with any of these problems 1 through 6?
For I got same stuff, but I ended up getting like 4 9.
Oh.
So yeah, maybe 9 or 9.
Okay.
Yeah, forgot to make the first term negative.
Yeah, I think you could get away with leaving your answer like this as long as you can claim that it's a value, whether you know it's positive or negative. And being able to make that justification. All right. Tomorrow, I will work through the 2019 FRQs that I didn't get to do in class. So I may jump around between problems for tomorrow's help session. All right, thanks, guys. See you tomorrow.
Thank you.
Thanks, Sean.
Thank you.
Thanks, tomorrow.